Okay, so we're going to be looking at the concept of pressure now. We'll look at the equation for pressure in P15, which is the next video, but just for now, just think of pressure as essentially particles colliding with the walls of their container, okay, which means a high pressure means more collisions per second. Okay, so particles obviously have got some kinetic energy, and obviously when they hit one of the walls of the container, obviously they're going to exert some pressure, they're going to exert some force over that particular area. Which means if we increase the temperature of a gas, it means the average speed of the particles also increases. This means that the pressure will also increase because the particles are colliding with the walls of the container more often. Okay. Now we're going to look at a concept, or what we call absolute zero. Now this is the coldest theoretical temperature that any substance can reach, okay? It has a value of minus 273 degrees Celsius, okay? Now physicists call that temperature 0 Kelvin, okay? And for your exam, you need to be able to convert between the two. So to convert from Kelvin to Celsius, we subtract 273, and if we're going to go from Celsius to Kelvin, we add 273. So make sure for your exam you're able to convert between these two units, okay? Now, in terms of using the specific heat capacity equation here, notice it is change in temperature, so it actually doesn't really matter if your values are in Kelvin or degrees Celsius, as long as you've got both in either one of them, okay? But obviously if the exam question is asking you to just convert from Kelvin to degrees Celsius, make sure you've got this conversion here. So what is absolute zero? Well, as I said, it means that the gas would have a pressure of zero. Because if we look at this, this graph here, okay, we've got pressure on the y-axis, we've got temperature on the x-axis, okay, and we know as we reduce temperature, okay, we're taking thermal energy from the particles, which means they're going to vibrate less, okay? Now if we continued that trend, okay, so if we continue to reduce temperature, the amount of kinetic energy is obviously being reduced, which means collisions on the side walls of the container is also being reduced, okay, up to a point when the particles should theoretically not be moving, okay, and we call that point absolute zero, okay? So scientists have backtracked, and that's how we've come to this value here, okay? Gas particles move in random directions, okay, as we've stated before, and they move at a range of speeds. Now obviously that means they're going to reach the walls of the container at a variety of angles, okay? But what we do actually, we're going to say that an overall force is going to be actually exerted, and this is going to be at right angles to the side of that container. So it's essentially the average force being exerted, and that's due to the average amount of angles with which those particles are actually approaching that container. Okay, so just make sure that you know that the overall force is at right angles to the side of the container, and then we can work out the pressure that those particles exert. Okay. Now, if a gas is at a constant temperature, the average speed of the particles will also be constant. Okay. If we decrease the volume of the container, the gas particles would hit the container more often. Why is that? Because obviously we're reducing the amount of wall space that those particles can hit. So if we've got the same amount of particles, the collisions essentially have less wall space to hit, which means we're going to have more collisions. So that means we're going to have a higher pressure. Okay. If we increase the volume of the container, the gas particles would hit the container less often. Okay, which means less pressure. That's simply there's more of the water hit, and essentially we've only got a certain amount of particles with a certain amount of kinetic energy, so that's why we're going to have less pressure. So let me just talk about this diagram here. Okay, so we've got a plunger which can move upwards or downwards depending on the pressure of the gas. Okay, so the internal pressure of the gas, let's say, I don't know, it's a certain amount of pressure. Now, if we were to somehow heat up that gas internally, that would obviously increase the kinetic energy, the movement of the particles, which means the pressure being exerted on the walls of this container plus on the plunger would be increased. That would mean that the plunger would move upwards and the volume would also increase. Now, if we increase the external pressure, okay, so that means we're now going, well, let's say we could use the mass here, that's obviously going to push down against the plunger towards the gas. That is obviously then going to reduce the volume of the gas, but as we said before, there's less wall for the gas particles to hit, which means the pressure is also going to increase because we've still got the same amount of particles, they're just being condensed into a smaller volume. Okay, so we're going to talk about the concept of conservation of energy. If we required thermal energy to heat up the gas particles in order for its pressure to increase, so that we would work against this mass to cause the plunger to move upwards, okay? So that thermal energy initially being passed onto the gas particles, kinetic energy causing movement of the plunger upwards, okay? The same thing, the weight of the force from the mass is going to push downwards, okay? So we've obviously got that kinetic energy moving downwards, which is obviously going to reduce the volume of the gas, which means we're going to have more collisions per second, which means we're going to have higher pressure, which effectively means our temperature of the gas is also going to be increased, which means the thermal energy of the gas will also increase when that plunger goes downwards. Okay, so that initial kinetic energy of the plunger will be transferred into thermal energy of the gas particles. Okay, and this is what happens inside a bicycle pump. Okay, so the average speed of the particles increase, and this means that the temperature increases when that plunger obviously falls down. Okay, due to that force, the weight from the mass. Okay, so it's again the conservation of energy. And then finally, I want to talk about this equation here, which you won't need to remember, but you just need to be able to use in your exam. And it talks about two states, okay, of the gases, volume and pressure. So the pressure at the start, which is the one denoted by the ones, okay, multiplied by the volume at the start, okay, has to equal the pressure at the end times the volume at the end, okay? So again, let's say, I don't know, we didn't have this mass at the start, we recorded the pressure, and the units are pascals, so we're going to be looking at the equation for pressure in the next video, but the units for pressure are pascals, or newtons per meters, but we're going to record the pressure at the start, we're going to record the volume of the gas at the start, then we now put our mass, okay, so obviously that means our volume changes, and then our pressure will change, and then we can record the pressure at the end, and then the volume at the end. And the product of both, provided no gas escapes, should be the same, okay? So again, in your exam, you could be asked to work out one of these unknowns and they would give you the other three. And that's the end of P14.